My friend Marcus can see things close to him very clearly, but far away objects not so clear. We say he is short-sighted. Because he can see things which are close to him, short-sighted. On the other hand, my friend Julie has the exact opposite problem. She can see things far away very clearly, but the close objects not so clear. We say she is far-sighted, because she can see things far away clearly. So let's figure out what defects in our eyes cause these behavior. Now, before we get down to it, let's first quickly recap how a normal undefected eye works. In a previous video, we saw that if your eyes were looking at something very far away, say this tree which is extremely far, this lines are saying that it is not to scale, the tree is kept very far away, then the rays of light from that tree would be pretty much parallel to the principal axis. And remember, in order to see something very clearly, the rays of light must always get focused onto the retina. And as a result, this now is the principal focus of our eye, because a parallel ray must pass through the principal focus. But as the object comes closer, say looking at Batman who's standing pretty close to you, then again, to see him clearly, the rays of light must again get focused onto the retina. But to do so, can you see now the new principal focus is over here, which means the principal focus has come closer. That means the focal length has become shorter. So as the object comes closer, the focal length gets shorter. And this happens due to the ciliary muscles. You've seen that the ciliary muscles are the one that can push this lens and make it more curved, increasing its converging power. But of course, we're going to ignore that to keep things simple. It's happening, but we'll not show that. But there's a limit to how small the focal length can be. So at a particular distance, let's say at this position, the focal length of our eye becomes minimum, which means it cannot become any smaller. And as a result, if this object were to come even closer, then you can't see it clearly. And we call this point as the near point, which is represented by D. So the key thing to remember is as the object distance changes, our eyes will adjust its focal length. It can take a range of these focal lengths. This, by the way, will be the maximum focal length. And because of this, it will ensure that the rays of light will always focus onto the retina. And if you need more clarity on this, it would be a great idea to go back, watch that video, and then come back over here. Alright, now let's come to the defective eye. So what causes these defects in the eye? Well, the short answer is the power of the lens is a little bit higher than usual or a little bit lower than usual. We'll look at why and how that happens a little bit later, but let's explore these cases and see what happens. So let's consider the first case as the power of our lens is a little bit higher than usual. So let's say high power, a little bit high power. What would this mean? This means our lens has more than usual converging power. In other words, it will have smaller focal lengths than in normal eye. In other words, the range of focal lengths that this eye can accommodate to will be smaller. All these values will be smaller than what a normal eye does. Alright, so now let's look at what happens when we keep an object close to us and what happens when we keep an object far away. Consider an object which is close to us. Say Batman standing close to us. If we draw rays of light, then a ray through the optic center will go undeviated, and the ray parallel to the principal axis, well, in order to see this Batman clearly, this ray must meet up with the other ray, and they should focus right at the retina. And the question is that possible? And the answer is yes. Our eyes can easily do that, because to do this, the required principal focus lies within the range that it can take. And so there is no problem looking at things close to us. But what happens when you're looking at things very far away? Say we're looking at this faraway tree again. The rays of light are pretty parallel to the principal axis. Again, the ray passing through the optic center goes undeviated. And in order to now see it clearly, this ray should again meet up at the retina. Alright, they should get focused at the retina. But is this possible? The answer is no. That cannot happen, because in order for this to happen, the principal focus of our eye must lie here, outside the range. Our eyes will not be able to accommodate to increase its focal length beyond this value. And as a result, what will happen? Our eyes will try its best and it'll just have maximum focal length over here. This is what will happen. And as a result, can you see that the rays are being focused in front of the retina? So we say the image is formed in front of the retina. And so this will look blurred to us. So notice, because of high power, we are able to see things which are close to us, not a problem, but we're not able to see things which are far away. In other words, this is the reason for nearsightedness. So we just discussed is nearsightedness or short-sightedness. Short-sightedness. The biological name for this is myopia. So the next question is, how do we correct this? You may already know that people wear spectacles or contact lenses. These are just converging or diverging lenses. So I want you to pause the video and think about what lens would you put in front of the eye? Would you put a converging lens or a diverging lens to correct this? All right, if we use a converging lens, then you can see it will increase the overall converging power. That means the rays of light will get converged even closer. That is making situation even worse. So we need to use a suitable diverging lens so that the rays of light on our eyes will be diverging and become easier to focus them back onto the retina. There are a couple of other ways to think about this. One way is to think that because we're adding a diverging lens, we are reducing the overall converging power, and as a result, we are increasing the overall values of the focal length back to normal. Another important way to think about this, especially for numericals, is that now the rays of light which are diverging, well, they appear to come from somewhere over here, somewhere close by, and our eyes have no problem focusing them on the retina. So either way you think about it, a diverging lens of suitable focal length will solve this problem. Now let's look at the other problem. What happens when our eyes have lower than usual power? Well, the analysis is similar. Now that our eyes have lower power than usual, it means the rays of light will get converged farther than usual. That means all these values of focal length would be higher than usual. So all these values will be a little bit higher than what we have. Okay? Now it would be a great idea to pause the video and try this out yourself. See what happens when the rays of light are coming from far away. See what happens when the rays of light are coming from close by. And see which of them will get focused nicely. All right, let's do this. If the rays of light are coming from far away, can our eyes focus it? The answer is yes, because our focal length is within that range. But what if the object comes closer? Let's say when Batman is standing close to us. Can it be focused? The answer is no, because notice in order to focus this ray now, the principal focus has to be at this point, which is lower than the minimum value. That's not allowed. Our eyes will try its level best, but it can only decrease the focal length to this value. And as a result, notice the rays of light are being focused behind the retina. And as a result, you can't see things which are close to us, but we can see things which are far away. In other words, this is the cause for far-sightedness. The biological term for this is hypermetropia. Hypermetropia. And again, pause the video and think whether we should use a converging lens or a diverging lens. Well, this time our eyes have lower than usual power, which means we need to increase its converging power. We have to use a converging lens, a convex lens of suitable focal length, so that it will help it converge the beam of light back onto the retina. And that's how we can solve the problem of farsightedness. Well, one last question we might have is what really causes this higher than usual power or lower than usual power? Well, it turns out there are multiple reasons. One of the reasons could be that the eye lens itself has more curvature or less curvature. For example, over here, it has low power because the eye lens over here has less curvature. I've exaggerated over here, and similarly over here, it will have more curvature. Again, an exaggeration, but that could be one of the reasons. Another possibility is that these lenses might be fine, but the eyeball over here is longer than usual, and this eyeball might be shorter than usual. But whatever it is, there are very common problems and they can be easily solved by using appropriate lenses. Now, the best part of this is we don't have to remember any of this because all of that can be worked out just by drawing ray diagrams like we did in the video. So all I remember is that these defects are caused either due to the high power or low power, and then we can just work it out to figure out which causes which, and then logically understand which lenses to use to correct them. And that's why I love ray optics.